In this video lecture, we're going to talk about section 6.8. This deals with improper integrals. So for what we've been doing with integration, we have considered integrals of the form integral from a to b of f of x dx when f of x is continuous on a finite interval a to b. Okay? So it's just been a nice, smooth, continuous function over some interval a to b. So the idea of an improper integral is if there is some sort of discontinuity occurring somewhere. Okay? So improper integral is an integral that has a discontinuity in a to b, or the interval is not finite, i.e. we're looking at the integral from a to infinity of f of x dx. Right. So if either one of these things is true, we call this an integral that is improper. Okay? There are a couple different cases. So let's look at type 1. So case 1. This is case 1. So let's say we have an infinite interval of integration. That is, we're looking at the integral from a to infinity of f of x dx, or integral from negative infinity to infinity of f of x dx, or the integral from negative infinity to b of f of x dx. So the interval on which we are integrating is infinite. Case 2 is discontinuity. At the endpoints, or within the interval of integration. All right. So let's look at case 1 first. So example, consider the integral from 1 to infinity of 1 over x dx. Okay. So let's graph this region. So if we were to actually, let's do 1 over x squared. That is 1 over x squared. So let's graph this function. The function, if we were to graph in the graphing calculator, looks something like this. So there is an asymptote at x equals 0, but we're looking for the integral from 1 to infinity here. So let's say this is 1. We're looking to calculate this area here. Okay. All right, so what we want to do is, because we can't plug in infinity, what we try to do is represent this integral as using some limit. So we're going to take x to infinity on the upper bound here. So I'm going to rewrite this integral from 1 to infinity of 1 over x squared dx. This is equivalent to the limit as, let's say, b goes to infinity of the integral from 1 to b of 1 over x squared dx. So we're just going to send b to infinity here. Okay. So let's see what we get. So we can anti-differentiate 1 over x squared, limit as b goes to infinity, of the antiderivative of 1 over x squared. Well, this is x to the negative 2, so we increase and divide. So that would be negative 1 over x from 1 to b. Okay. So continuing that, so we're going to leave the limit to the very end, so we'll rewrite that limit as b goes to infinity. Now let's use the fundamental theorem of calculus on this. That would be negative 1 over b minus negative 1 over 1, which would become a plus, right? So we're looking at the limit as b goes to infinity of negative 1 over b plus 1. Now if we evaluate, if we plug in infinity here, we'll get negative 1 over infinity plus 1. Well, what is negative 1 over infinity? Well, this is negative 1 divided by a super large value. This is 0 plus 1. Right? So we can see here that even though our area is like infinitely long, it does go to a value. Okay. So here we say that the integral from 1 to infinity of 1 over x squared dx converges to 1, since the area is finite. Okay? We're talking about this area converging to 1. Do another one. Let's look at this example. So we're going to consider the integral from 1 to infinity of 1 over x, no square this time. Okay. So again, let's graph it. 1 over x looks something like this. And we're looking at the area between the curve and the axis from 1 to infinity. So similar to the last one. In fact, this curve here is actually a little higher than the previous one. So let's do the same analysis here. So this is integral from 1 to infinity of 1 over x dx is equal to, let's write it as a limit as b goes to infinity. The integral from 1 to b of 1 over x dx. All right. Now let's take care of the integral. Keep our limit. So the antiderivative of 1 over x is the natural log of absolute x from 1 to b. Now evaluating, get limit b goes to infinity of the natural log of absolute b minus the natural log of absolute 1. Now, since b is positive and the natural log of 1 is 0, this boils down to finding this limit. The limit as b goes to infinity of the natural log of b. Okay. So now let's think. What is this limit? If we put in infinity, what's happening with the natural log function as x gets very, very large? Well, if you consider the graph of the natural log, that looks like this. All right. So graphically, one can see that the natural log function, as x gets large, just continues to increase. So this limit is infinity. So here we say the integral from 1 to infinity of 1 over x dx diverges since the area is infinite. Okay. So you can see just a change in the power at the bottom kind of changed the outcome of our situation. Okay? So the integral from 1 to infinity of 1 over x squared converges, but the integral from 1 to infinity of 1 over x diverges. Alright, let's take a look at another example. Let's do case 2 now. Case 2 dealt with discontinuities or asymptotes at the endpoints or within the interval. Alright. So let's try this one. How about the integral? The integral from 2 to 5 of 1 over the square root of x minus 2. Alright, so what we're doing here, if we notice, this is improper because the function has an asymptote at the lower endpoint here. 2, this function will have an asymptote. So what we can do is rewrite this using a limit. Let's say limit as a goes to 2 from the right. Okay, so this is the lower endpoint, so we need to approach from the right. Of a to 5, 1 over the square root of x minus 2 dx. Alright, so let's anti-differentiate this. Well, we can use a u substitution. So we're going to let u equal x minus 2. So du is dx. Now our bounds, the upper bounds will be 5 minus 2, which is 7. And the lower bound will be a minus 2. So here we have the limit as a goes to 2 from the positive side. Integral of a minus 2 to 7 of 1 over the square root of u, or u to the negative 1/2. So let's take care of this antiderivative. Keep your limit. increase and divide. So negative 1/2 plus 1 is positive 1/2. Divided by 1/2 will give us 2. So this is 2u to the 1/2 from a minus 2 to 7. So we're looking at the limit of 2 times 7 to the 1/2 minus 2 times a minus 2 to the 1/2. Right, so we know that this is just some value, okay? 2 root 7. 2 root 7 minus, now let's take our limit here. If we put in 2, right, we're taking the limit as a goes to 2. If we put in 2 here, what do we get? 0. Gives us 2 root 7. So here we say the integral converges, right? This integral converges because we get a number instead of infinity. All right. Let's try another. Does the integral from 0 to 1 of 1 over x minus 1 converge or diverge? Right, so you can see here this is improper, right? It's improper because we try to plug in 1, we get a 0 in the denominator. So let's set up our limits. The integral from 0 to 1 of 1 over x minus 1 equals the limit as, since this is the upper bound, let's use b. b goes to 1 from the left side. We're approaching from the left as we sweep across the interval. 0 to b. 1 over x minus 1. So we know from our partial fraction lectures that the antiderivative of this guy is just the natural log, right? So this is equal to the limit as b goes to 1 from the negative side. Natural log of absolute x minus 1 from 0 to b. So that is the limit as b goes to 1 from the negative side of the natural log of b minus 1 minus the natural log of 0 minus 1. Alright, so let's try to evaluate this now. So here we have the limit, so 1 from the negative side is going to go in. Here we have the natural log of 0 minus 1 absolute value. So 0 minus 1 is negative 1, absolute value of that is 1. We know the natural log of 1 is 0. So this guy is 0. So all we need to do is look at the limit as b approaches 1 from the negative side, the natural log of b minus 1. Okay. So let's think about what's happening here. As b goes to 1 from the negative side, what does this value become? Well, this value approaches 0, right? So because b minus 1 approaches 0, we're looking to see what the natural log is doing as we approach 0. So let's consider the graph of the natural log. Graph of natural log function looks like this, right? So as we approach 0, what do we get? Negative right? Negative infinity. Right. Therefore, this integral diverges. Okay, so that takes care of that. Let's try more. Example, determine if the following converge or diverge. A. About the integral from negative infinity to 0, x e to the x dx. Alright, so we notice that this is an improper integral because it is an infinitely long interval of integration here. So let's rewrite this as a limit. So it's the limit as, well, here's a, right? So a approaches negative infinity. Integral from a to 0 of x e to the x dx. Alright, so now we need to evaluate this. So what technique of integration looks useful here? And that would be integration by parts, right? So by integration by parts, our u is x, our dv is e to the x dx. So du is 1 dx, and v is e to the x. So the limit as a goes to negative infinity of, use your integration by parts formula, x e to the x from a to 0 minus the integral from a to 0 of e to the x dx. We can evaluate the second integral fairly simply, so let's just write it all as one evaluation. So we get x e to the x minus e to the x from a to 0. So, evaluate at 0, we'll get 0 minus 1. So limit a goes to negative infinity of 0 times e to the 0, that's 0, minus e to the 0 is 1. So that would be negative 1 minus, now a goes in, so that would be a, e to the a, minus e to the a. Alright, so let's evaluate limit as a goes to negative infinity of negative 1 minus a e to the a plus e to the a. So let's look. What's the limit as a goes to negative infinity of negative 1? Well, it's just not dependent upon a, so that's just going to be negative 1 minus, what's the limit as a goes to negative infinity of this guy? Well, that's a little hard, so let's skip that for now. Plus, what's the limit as a goes to negative infinity of e to the negative infinity? There. So we have to investigate a couple of limits here. So first off, let's do this one. This one's not so bad. So if we consider, so what's happening for the exponential function? So for this guy, y equals e to the x looks like that, right? So if we go towards negative infinity, this function goes to 0. So this is 0. Right? Now the limit as a goes to negative infinity of this thing here. Well, we need, if we plug in negative infinity, that's not going to give us much of anything. So what we can do is use L'Hopital's rule. Try to. So this is equivalent to, if we sink that e to the a down, that would be a over e to the a, negative a, that is. If you think about plugging in negative infinity, if negative infinity goes in, we'll have negative infinity over, negative infinity goes in here, that would be e to the positive infinity, which is infinity. So that's an indeterminate form for our limit. So let's take the antiderivative, or the derivative of each top and bottom, using the L'Hopital's rule. Limit a goes to negative infinity. The derivative of a with respect to a is 1 over the derivative of e to the negative a with respect to a is negative e to the negative a. So we'll get negative 1 minus this limit. Now let's plug in. 1 over negative e to the infinity. That's 1 over infinity. That is 0. Therefore, our answer is negative 1. So this guy converges. Let's do integral from 0 to the natural log of 2 of e to the 1 over x squared dx. Okay. Is this improper? Well, it is, right? We can't plug in 0 in either case, right? There's a discontinuity at 0. So let's write it as limit. This will be limit as a goes to 0 from the right. Integral from a to the natural log of 2 e to the 1 over x squared dx. So how do we take care of this antiderivative? Well, let's think. Which of our techniques is useful here? Well, notice that we have a 1 over x here. What is the derivative of 1 over x? Well, that's negative 1 over x squared, so we have that here, right? So we can do a u substitution. U equals 1 over x. du is negative 1 over x squared dx. And we want this to be positive, so negative du equals 1 over x squared dx. Okay? Alright, so let's go ahead and get our bounds as well. So our upper bound becomes 1 over the natural log of 2. And our lower bound becomes 1 over a. So you have the limit. A goes to 0 from the positive side. Integral of 1 over a to 1 over natural log 2. We have a negative happening for our du, so let's say negative 1 over x dx is taken care of by negative du. So all that's left is e to the u. Negative e to the u. So what's the antiderivative of negative e to the u? That's negative e to the u. Limit a goes to 0 from the positive side. Negative e to the u from 1 over a, so 1 over natural log 2. Let's see what we get. Using the fundamental theorem, let's just plug in. Negative e to the 1 over natural log of 2 minus negative, so plus e to the 1 over a. Alright. So we need to evaluate some limits. So the limit as a goes to 0 for this guy. Well, this is just some weird number, right? So we can just pull him out. So that's just a weird number. Plus the limit as a goes to 0 to the positive side, e to the 1 over a. Right, so all we need to do is figure out what this limit is. So let's think about it. If 0 goes in, e to the 1 over 0, what's 1 over a really small number? 1 over a small number is a big number. So this is e to some really big number. So that is infinite. Once again, 1 over 0.01 is, 1 over 0.01 is 100. Now, let's make it smaller. 1 over 0.00000001. Well, that's that really big number. So as the a value goes closer and closer to 0, that value gets bigger and bigger and bigger, and e to this number is even much bigger. So that's infinitely large. Therefore, our answer is infinity. So this diverges. Let's do one more. Let's see. So this is the integral 2 to infinity of 3 over x squared minus x dx. Alright, this is like a case 1 type, so we have infinitely long interval of integration, so that's improper. So we need to write this as a limit. The upper bound is the infinity, so let's say that's b goes to infinity of 2 to b. 3 over x squared minus x dx. Okay. Now let's evaluate the integral. So how do we evaluate integrals that look like this? Well, run through your list. Is u sub work? No. Is integration by parts going to work? No. In fact, this is a partial fraction decomposition problem, right? So let's do our partial fraction decomposition over here. Alright, so we have 3 over, we need to factor that. So that would be x times x minus 1 equals. So split it into partial fractions, a over x plus b over x minus 1. And let's get them back together. So here we would have 3 equals a times x minus 1 plus b times x. Or 3 equals, collect your x's and your constants. A plus b, and negative a. So what do we know? A plus b, there's no x term here. A plus b has got to be 0. And negative a is equal to 3. So a is 3, and b will be negative 3. So coming back up here, we have the limit. As b goes to infinity, integral 2 to b of 3 over, excuse me, a is negative 3, b is positive 3. So negative 3 over x plus 3 over x minus 1. This is equal to, so we know that these are natural log derivatives, so limit b goes to infinity, negative 3 natural log of absolute x, plus 3 natural log of absolute x minus 1, from 2 to b. Alright, so let's take a look here. So we'll have the limit as b goes to infinity of negative 3 natural log of b, and b is positive, so we can get rid of the absolute. 3 natural log of b goes in. We know that b is larger than 1 as well, so we can get rid of the absolutes there too. Minus negative 3 natural log of 2 plus 3 times the natural log of 1. Alright, so what do we get? Well, we know that this guy is 0, so we'll have a positive 3 natural log of 2 coming out, plus this limit right here. So if b goes in, if infinity goes in, that is negative infinity, right? Because natural log goes to infinity, so if natural log of infinity is infinity, that would be negative infinity plus positive infinity, right? It would be negative infinity plus positive infinity. So note that that is an indeterminate form. So we have to work around that a little bit here, because we have the addition of a negative infinity and a positive infinity. Now, negative infinity plus positive infinity is not necessarily 0, because some infinities are larger than others, right? For instance, how many counting numbers are there? So 1, 2, 3, there are infinitely many of them, right? But how many integers are there? So the integers include the counting numbers plus all the negative counting numbers. So that infinity is larger. So that's why it's indeterminate here. So we need to work around that a little bit. So what I'm going to do first is factor off this 3 and pull that out of the limit. It's a property of limits you learned about in Calc 1. And I'm looking at, alright, this one first, negative natural log of b minus 1 minus the natural log of b, right? So we're already taking care of these terms. That's 0. That is positive, so that can be pulled out. Now I'm just rearranging this and pulling out that 3. So note that there's a property of natural logs that says the natural log of a difference is equal to the natural log of a portion. This property is always true. So we can actually rewrite this limit of the natural log of b minus 1 over b. So let's see what this limit is, right? So as b goes to infinity, the top goes to infinity and the bottom goes to infinity. In fact, we can write this as the natural log of b divided by b is 1 minus 1 over b. Right? So now let's reconsider. So we have 3 natural log of 2 plus 3 times whatever this limit is. So as b goes to infinity, what happens? So 1 over infinity, this guy will go to 0. 1 minus 0 is 0. And what's the natural log of, 1 minus 0 is 1. And what's the natural log of 1? Let's see. 3 natural log of 2 is converges. All right, so you have some examples of how to handle improper integrals. Go ahead and take a look at those examples in your suggested homework.